Greetings to StormWork 2023. As we board on a fresh week, our focus shifts to exploring 3D modeling, design considerations, and software tools tailored for 3D concrete printing. To kick things off, let's first speak about the modeling and design considerations or parameters related to them, specifically aimed at 3D printed objects. The design considerations which will be discussed now are not just for 3D modeling, but also applicable to slicing process. As a side note, slicing process refers to the process of converting a 3D model into a series of thin, two-dimensional cross-sectional layers that the 3D printer can understand and build upon layer by layer. This process involves slicing the 3D model into numerous horizontal layers, which are then printed one on top of the other to create the final three-dimensional object. Slicing software, often called slicers, take the 3D model in format like STL and slice it into layers. The software allows users to adjust settings like layer height, print speed, infill density, which is the amount of material inside of the object, and support structures for overhanging parts, but like this is more applicable for plastic printing. Each layer's information, including the path the printer's nozzle or layers need to follow, is translated into a Cartesian coordinate-based machine-readable instructions G-code that the 3D printer used to deposit or solidify the material layer by layer, gradually forming the physical object. Proper parameter setting according to the printing material property is crucial for the quality and structural integrity of the printed object in slicing process. Factors like layer height, printing speed can affect the surface quality, strength, and overall quality of the final 3D printed products. First, layer geometry. So this is like a first design consideration. Layer geometry in 3D concrete printing is a crucial aspect that significantly influences the structural integrity, surface quality, surface finish, printing speed, and overall quality of the printed object. The considerations regarding layer height, width, and the other geometric aspects are pivotal in the design process for successful concrete printing. Smaller layer height typically results in finer resolution and smoother surface finishes. A reduced layer height allows for more precise detailing and intricate designs. However, finer layers may require more time for printing, affecting the overall production speed. Layer height also impacts the structural integrity of the printed objects. Thinner layers often provide better bonding between the layers as the nozzle slightly compresses the depositing layers, enhancing the overall strength of the structure. It eventually helps in creating homogeneous and well-bonded layers, reducing the risk of delamination or structural weakness. Another parameter in layer geometry is layer width. Layer width refers to the horizontal dimensions of the printed layer. The final layer width is influenced by the extrusion rate, nozzle shape and size, printing speed, and overall geometry of the printed object. Wider layers allows for higher extrusion rate, enabling faster printing as it produces bulkier layers. However, this can affect the accuracy of the printed object, especially in complex design. Balancing the layer width with printing speed is crucial to maintain successful integrity and accuracy. Wider and higher layer width and height might be suitable for larger structural elements or rapid prototyping, while thinner layers are preferable for detailed and complex designs. Design considerations should account for the desired geometry and the printing constraints imposed by layer width. Secondly, nozzle cross-sectional dimensions. The shape and area of these nozzles cross-sections significantly influences the dimensions and geometry of the concrete filament. A round cross-section of different diameters or a square cross-section of different dimensions or rectangular shaped nozzle could be considered, In all these scenarios, the nozzle scale and cross-sectional design significantly dictates the layered geometry of the printed filament and consequently influence the printed elements of a structure. Thirdly, interaction of translation and rotation. Another impactful factor which diminishes as the scale increases involves the interplay between translational and rotational movements. When conducting printing tasks, it's crucial for the nozzle head to align tangentially with the tool pods to prevent layer twisting. To achieve this, robot Z-axis rotates to maintain the nozzle's head alignment where the tool pods, if the nozzle rotation is allowed. If the tool pod's curvature becomes excessively steep, the rotational axis cannot synchronize with the translational axis. This discrepancy results in erratic nozzle movement, impacting the filament quality. Furthermore, overly pronounced or sudden tool pods can induce vibrations in the end effector or machine itself. This degrades the print quality correspondingly. These issues can be mitigated by reducing the print speed, or ideally paired with the downsizing the dimension of the printed filament. Alternatively, scaling up the overall geometry can moderate the extremity of the curvatures. Next, corner curvature. The architect's initial design features sharp or pointed edges which needed to be altered to softer, blunt edges due to limitations in robot or gantry kinematics. The print head adheres to a tool pod. It is defined spatial route to achieve desired outcomes. This tool pod remains independent of specific dimensions, allowing the printer to move with precise accuracy along this trajectory, disregarding the dimensions of the printed filament. However, the concrete filament generally maintains a finite size, for instance, 10 by 40 millimeter in the rectangular shaped nozzles. Consequently, the radius of curvature differs between the inner and the outer curves. When executing sharp turns in the tool pod, such as a 90-degree angle, the materials deposited in the small inner curve tend to accumulate, altering the section dimensions of the filament. Simultaneously, the outer curve tend to expand, affecting the filament dimensions, potentially causing cracks or surface ruptures. With continuous layering, these areas accumulate, leading to tilting of the layers on one side, resulting in substandard or even failed prints before it's completed. And print in segments in joints. The dimensions of 3D printer's bed, say 9 meter by 5 by 3 meter, directly influence the size of the printable elements, necessitating their adherence to this scale. However, construction that demands elements larger than the bed dimensions must be printed in segments. Consequently, the design process must factor in the creation of joints or the assembly of these divided parts. And the final aspect is material behavior. The composition of concrete mixture significantly affects how it behaves during printing. The choice of aggregates, cement types, admixtures, and other additives directly impacts the material's viscosity and flowability, and the setting time as well. For instance, using fine aggregate makes the extrudates smoother, and while additives like the plasticizers or the superplasticizers can improve flowability and reduce the risk of clogging in the printing nozzles. As I have highlighted before, especially in Rig 2, the flow property of the concrete mixture are critical for consistent and precise extrusion. An optimal viscosity and flow rate are essential for achieving layer adhesion and uniform deposition. Proper flow behavior properties ensures that each layer adheres firmly to previous one, preventing delamination or weak bonding between layers. Design consideration here involves accounting for the material's flow behavior within the printer's constraints, adjusting geometry and path planning to ensure smooth extrusion without compromising structural integrity or plastic failure during printing. Material properties directly influence the design choices in 3D concrete printing. Designers need to consider the rheological behavior of concrete, which means how it flows, its viscosity, and thixotropic nature. When creating geometry, the curves, layer thickness and height, and so on. Sometimes you may need to modify wall thickness, curvature radii, or print parts avoiding reinforcement. As we conclude this segment exploring 3D modeling and design considerations, we've unraveled crucial insight into layer geometry, nozzle dimensions, and the material behavior when designing 3D modeling and slicing the model to create tool parts. Understanding these complexities becomes the cornerstone for success in leveraging 3D concrete printing technologies. Thank you for being a part, and see you in the next video.